So now we begin we continue what we on the method we continue the method of solving differential equations of order 2 that we did yesterday. So we arrived at page 6. So we have seen last time that if you have a differential a second order differential equation of this form, y double prime plus a1 x times y square y prime plus a2 x times y is equal to 0. So this is a second order differential equation, and I gave you yesterday a method that if you know a particular solution, say y1 of x, then you could deduce the second particular solution with this formula. So the second one would be like this. So y2 would be equal to y1 times the integral of exponential minus the integral of a1 x dx all over y1 squared dx. So you simply do this calculation and you find y2, and then the general solution of the equation, the second order differential equation, would be simply yg is equal to c1 y1 plus c2 y2, that is simply y1 the integral of exponential a1x dx over y1 squared dx. So this is the general solution that we are looking for. Now I will introduce to you we will talk about the special cases where the coefficients of the equation would be constants. That is the case where a1 of x is equal to some constant c1 and a2 is of x is equal to some constant c2. I will avoid this name because this name is c1 and c2, since we use them in the general solution. Let's call this as p, and this is q. So now I will show you how to solve differential equation of second order with constant coefficients, something like this. So sorry, here we have py is equal to 0. So this is a second order differential equation with the constant coefficients. Here the method of solution is very easy and simple. I will not dive into the details of how we get those solutions. I will give you only the method. I will upload, of course, to you the course online if you are interested in the steps on how we arrived to these solutions. Uh, who wants to talk? So, I will give you the method. You are asked to review the course I will upload later, and tomorrow, if you have any questions, you can ask them during the session. So, this is simply we have three cases. Uh, so, so if you suppose that the solution will be something like this: y is equal to some exponential kx. Now we will substitute this solution into this differential equation, name it star, and see what we get. So if you do this, you will find something like this. So exponential kx double prime plus p exponential kx prime plus q exponential kx is equal to 0. Now you know how to differentiate these three functions, of course, because it is exponential. So what we get? This, the double derivative of exponential kx will give you k squared times exponential kx plus p times k exponential kx plus q times exponential kx, which is equals to 0. Now we will factor out exponential kx from the three terms, and we get exponential kx times something like this: k squared plus p k plus q is equal to 0. Now since the exponential is always greater than 0, this term must be equal to 0. So we get the expression, the roots. So k, to find this k, we must solve this equation of second order, of second degree. So k squared plus pk plus q is equal to 0. I have to tell you that this is called, we call it the characteristic equation. This is called the characteristic equation. Now let's discuss the solution of this second degree equation. So we have three cases. We have three cases. Sorry. We have three cases. The first case is, I just said I will not dive in the details. Now I am getting myself, I found myself talking about the details. So this is it. This is what we did now is the method on how to arrive to these solutions. So now the case number one is for the characteristic equation we have two real solutions that are distinct. Here, the determinant of the equation, of course, it is bigger strictly than 0, which is the square root of, sorry, the root of the determinant is the square root of p squared minus 4q. Okay, this is the case. This is strictly greater than 0. Okay, it is not imaginary. So here we have two solutions. K1, let me remind you, it is minus p plus the square root of delta, which is p squared minus 4q over 2. And the second one is the conjugate solution. It is minus p minus the square root of p squared minus 4q over 2. So this is the first case. Here, of course, delta should be greater than 0 for both these two solutions. Now the second case, this is the first case that we will discuss. The second case is is when we have two complex solutions. That is, in this case, delta is less than 0. Here, simply the solution K1 would be something like this. K1 is equal to minus P plus E, the square root of 4Q minus P squared. It is the inverse of the determinant. So, and the second one is K2 is equal to minus P minus E times, I will simply write minus delta, the inverse of delta. Okay. Here delta, of course, is less than 0, delta is less than 0. And of course delta is p squared minus 4q. Okay. So this is the second case that we will discuss, and we have the final case, or the third case. Third case is simply you will have K1 is equal to K2 is equal to some real number minus P over 2. So we have multiplicity 2, and this is the case where delta is equal to 0, that is P squared minus 4Q is equal to 0. Now we will discuss in each case of the following these three cases how to construct the solution. So we move to the first case. So the first case Case 1. The roots of the characteristic equation are real and distinct. So the roots are real, distinct. K1 different than K2. In this case, the solutions are very simple. The two particular solutions we have: y1 is equal to exponential k1x, and the second particular solution is y2, which is exponential k2x. And the general solution, yg is simply a constant c1 times exponential k1x plus c2 exponential k2x. Okay, till now, is there any questions? Did you understand? Later I will give you the examples on how to apply this. So uh, uh, just wait a little bit. I will remind the others that the session is begun. Copy the link. Okay, we continue now. The second case. So case sorry case 2. The second case is when the roots of the equation are complex. The roots are complex. That is, we have k1 is equal to alpha plus e beta, and k2 is equal to some number alpha plus e beta. So in this case, here alpha, as we have seen before, is simply minus p over 2, and beta is simply equal to the minus the delta, the square root of minus delta over 2, or which is equal to 4q minus p squared all over 2. Okay, here the two solutions simply are y1 is equal to exponential alpha plus e beta times x, and y2 is equal to exponential alpha minus e beta times x. Okay, now we if you consider the solution, if we consider the solution as a if the solution is complex, that is y is equal to some function u of x plus e some function v of x. So if this solution, if this solution is complex, that is, it satisfies equation star, then uh, you will get something like this. uh, u sorry ux u plus e v double prime plus p times u plus e v prime plus q times u plus e v is equal to 0. By the rules of uh, since this is equal to 0, we will gather together the imaginary and the real part of this equation. So we should get something like this: u double prime plus p u prime plus q u plus e times the other part is v double prime plus p v prime plus q v is equal to 0. And remember, this is a complex number. For a complex number to be equal to 0, we should have its real part equals to 0 and its imaginary part is equal to 0. This means that we have two equations of this form. So u double prime plus pu prime plus q u is equal to 0, and v double prime plus p v prime plus q, sorry here q, qv is equal to 0. So these two functions should satisfy equation start, okay, that we have seen before. The first one is when we substitute u by u, and here we substitute u by v, okay. So these two functions, the real and imaginary part of the complex solutions, should satisfy equation star, which is the second order differential equation with constant coefficients, okay. So now next let us rewrite now the complex solution in the form of the sum of real and imaginary part. If so, u1 is equal to exponential alpha plus e beta x. So you will distribute, it will be something like this: exponential alpha x plus e beta x, and this would be exponential alpha x times exponential e beta x. And you know what this is, the exponential of a complex number is equal to, so we will get finally exponential alpha x times this function, which is cos beta x plus e sine beta x, okay. So this is the first solution, the first complex solution, and the second one is exponential. By the same reasoning, you will get exponential cos beta x, and here not plus but rather minus e sine beta x, since you know that this guy here is equal to exponential alpha minus beta e times x, okay. So these are the two solutions. Uh, According to what we have just demonstrated, the following real functions will be particular solutions of the equation 15. So the two particular solutions that we are looking for is, this is the first particular solution, is exponential alpha x times cos beta x, and the second particular solution is 2 exponential alpha x times sine beta x. Okay, and therefore the general solution would be something like this. It is c1 times the first solution, which is exponential alpha x times cos beta x, plus the second one is c2 times exponential alpha x times sine beta x. Okay, so this is the method of solving a differential equation of order 2 with constant coefficients. Okay, so we move to the third case. Sorry, here there is one more information about this case. If you have an equation, if you have an equation of this form, it is y double prime plus q is equal to 0. In this case you will get q1 and 2 are purely imaginary. In this case it is plus or minus e the square root of this guy here, which is q. In this case the solution will be reduced to, the general solution is y is equal to c1 times cos beta, simply beta x, plus c2 times sine beta x. That is, or simply you could, this is because this is times 1, which is exponential 0 times x. Okay, here p over 2 is equal to 0. Okay, now we have the the third case, case number 3. Here we have a real double root. So in this case the solution simply if you suppose that you have, so we have in this case k1 is equal to k2 some real number or imaginary number. Okay, in this case what we how to get the second solution, we know that we have the first solution is something like this, is exponential k1x, but we have the k1 is equal to k2, and the first particular solution and the second particular solution should not be linearly dependent. So how to figure out the second solution? To do this, let's suppose that the second solution u2 is some function u of x times the first solution, which is k1 exponential k1x. Okay, so if you derive this, you will get something like this. It is here u prime exponential k1 x plus k1 u exponential k1 x. Next, if you take the second derivative of u2, you will find something like this. You will derive this again and you will get so this is actually equal exponential k1x times u prime plus k1u. Okay, if you derive again, you will differentiate again, you will get something like this exponential k1. I will give you directly the answer. It's simply an algebraic operations, so you will get something like this u double prime plus 2k1 u prime plus k1 squared u. Okay, now if you substitute the into our second order differential equation, what you get is something like this. So we have y2 should satisfy the differential equation, that is y2 double prime plus p y2 prime plus q y2 is equal to 0. Now if you substitute, you will get exponential k1x times u double prime plus 2k 1 plus p times u prime plus k1 squared plus p k1 plus q plus p k 1 plus q u is equal to 0. But this guy here is equal to 0, and this one is equal to 0. Why? Because simply k1 is double root of the characteristic equation. We have this is the characteristic equation of the characteristic equation. So this is the characteristic equation, and we know that k1 is a solution to the characteristic equation, so this should be equal to 0. And also sorry, and also because k1 is equal to minus p over 2. Remember this, because here we have delta is equal to 0. Remember that k1, when delta is equal to 0, that the solution of the characteristic equation takes this form. This will give you that 2k1, and you take p is equal to minus p, and therefore 2k1 plus p is equal to 0. Okay, and this is exactly this guy right here. So what is left is this. So finally we will get something like this. We conclude that exponential k1x times u double prime should be equal to 0. But remember that this guy here is always greater than 0, so this u double prime should be equal to 0. So u double prime of x is equal to 0. We will solve this second. This is very easy to solve. Simply we take the first integral, we get u prime is equal to the integral of 0 dx, which is simply a constant c. Call it sorry. So what we will call this first, we call it, for example, this is C1. The first constant is C1. So we have now u prime is equal to C1. Now we take the second integral. So u is equal to the integral of u prime dx, which is the integral of c1 dx, and in this case you will get c1x plus another constant c2. So finally we get u is equal to c1x plus c2x. Now we will replace this. We will replace this in the second solution. So since u2 is equal to ux times the first solution, which is u1, so you get something like this: c1x plus c2 times exponential k1x. So if now now the general solution is so the general solution would be simply this guy right here. Okay, so why? Because uj is for example name this c prime y, for example, times y1 plus c2 prime times y2, and if you substitute you will get something like this. It is c1 prime u1, which is exponential k1x plus c2 prime times this guy here, c1x plus c2 exponential k1x, which finally, when you factor out k1x, you will find something like this: c1 prime plus c2 prime c2, this is a constant, plus c2 prime c1x. So to simplify, we will simply rewrite this as this is a constant and this is a constant. So briefly, we will suppose that the general solution is simply something like this. It is k1x times a constant c1 times a constant c1 plus a second constant c2 times x. Okay, so this is the general solution if we have double roots of the equation. Okay, so now we move I think we have seen how to solve the second order differential equation with constant coefficients. We move now to the exercises of the second series. Do you have any questions till now? So I will continue. Yes, let's check our series of exercises. So last time we arrived at exercise number 4 about Bernoulli's equations, and we solved the equation 1 and equation 2 we solved also equation number 3, and did we solve the equation number 4? Someone answer, please. Rayla, did we solve the problem number 4 of exercise number 4? So, and problem number 3 of exercise 4? We did 2, number 2, and 3. So, so for the moment, let's go to exercise number 6. Then we return back tomorrow, or maybe I will just give you the solution since it is the same method of the remaining problems of exercise 4 and exercise 5. So we will go to exercise number 6. So here, exercise. So exercise, sorry. So exercise number 6. So the exercise, find the general solutions to the following equations. So the exercise is find the general solutions to these differential equations. So equation 1 is y double prime. It is y double prime. Sorry, I have to change the color. Y double prime minus 6y prime minus 6y prime plus 5y is equal to 0. So this is the simply the equation, y double prime minus 6y prime plus 5y is equal to 0. So how to solve this equation? How to solve this equation? This is very easy. We apply simply the what we have done till now. We compute the characteristic equation. So the characteristic equation is, so remember, the characteristic equation is this polynomial k squared minus 6k plus 5 is equal to 0. Now what is the solutions of to this equation? We compute delta. Delta is equal to minus 6 squared minus 4 times 1 times 5, which is equal to 36 minus 4 times 5, which is 20, which leave us with 16. So the square root of delta is square root of 16, which is 4. So here delta is greater than 0. So literally we have two solutions, k1, which is 6 minus the square root of delta over 2. So in this case it would be 6 minus 4 over 2, which is So 2 over 2, which is 1. And k2 is equal to 6 plus the square root of delta over 2, which is 6 plus 4 over 2, which is equal to 10 over 2, which is 5. So we have two roots. We have two distinct real roots. K1 is equal to 1 and K2 is equal to 5. So the solution, what is the solution now? You have all the informations. So the solution, can you answer please? So the solution is simply the general solution yg is constant c1 times exponential the first solution, which is k1x plus c2 exponential k2x. Therefore it would be c1 exponential x plus c2 exponential 5x. Okay, so this is the general solution to this equation, to the equation y double prime, sorry, what is the equation again? Minus 6 y prime plus 5y equals to 0. So this is the solution to this equation. You could verify it. We will do it only this time, but for the other cases we will accept it as the solution. So this is the first time we will check if this is really the solution to this equation. Let's substitute. If you substitute, notice c1 exponential x plus c2 exponential 5x, this double prime, minus 6, same thing, c1 exponential x plus c2 exponential 5x prime plus, plus or minus, plus 5, plus here, plus 5, plus 5 y, which is c1 exponential x plus c2 exponential 5x. Now what this is equal to? So it is equal to c1, the exponential double prime is exponential x, plus c2, the second derivative of exponential 5x is 25 exponential 5x, minus 6 c1, the derivative of exponential x, it is exponential x, minus 6 times c2, the derivative of 5 exponential 5x is simply 5 exponential 5x plus the 5, the remaining c1 exponential x plus 5 c2 exponential 5x. So now we will collect the exponential x together and the others together. So exponential x, this guy here, and we have this guy here, and we have this guy here. So we have c1 minus 6 c1, and here we have plus 5 c1, okay, plus next exponential 5x times, now we will factor out exponential 5x. So this is our first guy. I will change the color. So this is the guy that we are looking for now, and this one. So we collect the coefficients. So here we have c2 times 25. So it is simply 25C2. And we have also here minus 6 times 5, which is minus 30. Minus 30C2. And here the remaining one is 5C2. So plus 5C2. Now do the algebra. So this is exponential x. C1 plus 5C1, it is 6C1 minus 6C1. And the other guy is 25C2 plus 5C2 is 30C2 and minus 30C2. So this is actually equal to 0 and this is actually equal to 0. What we left, so everything is equal to 0. So indeed the general solution is correct. So it is C1 exponential x plus C2 exponential 5x. Okay. Now we move to the next equation. Is there any questions till now? Is it clear? So the next equation is y double prime minus 4y prime plus 4y is equal to 0. So you have here problem 2. Problem 2, so we have y double prime minus 4y prime minus 4y prime plus 4y is equal to 0. So the first step is simply to calculate the characteristic equation. So the associated characteristic equation is k squared minus 4k plus 4 is equal to 0. So this gives us delta is equal to minus 4 squared minus 4 times 4, which is simply 16 minus 16, which is equal to 0. So delta in this case is equal to 0. So we have double root. So k is equal to, here it is minus 4 over k1 and k2 is equal to minus 4 over 2, which is minus 2. You could verify this. So minus 2 squared is 4 and we have 4 plus 4 is 8 and sorry, it is 4. Sorry, here the real solution is 2. Okay, so this is a double root. So we will deal with it. It is double root k equals 2. So this is the second, this is actually the third case. How to solve it? As we have seen in the third case, we will simply, the solution would be simply, the general solution is yg is equal to exponential 2x times c1 plus c2x, and that's it. This is the solution that we are looking for. So it is very easy to solve differential equations of order 2 with constant coefficients. So any questions till now? We will move to the next. So equation problem number 3. Sorry. So problem number 3. We have too many problems today. So y double prime minus y prime plus y is equal to 0. And in this problem we have initial conditions. That is, it is required from us to compute C1 and C2. So the problem 3 is an initial condition problem. We have y double prime minus y prime plus y is equal to 0. And we have the initial conditions too. y0 is equal to 1 and y1 of 0. Yes. So it is initial conditions are y of 0 is equal to 1 and y prime of 0 is equal to 2. Okay, so this is the problem. Now we will solve it. So we compute delta. So the characteristic equation is k squared minus k plus 1 is equal to 0. Here delta is minus 1 squared minus 4 times 1 times 1, which is equal to 1 minus 4, which is equal to minus 3, which is less than 0. In this case, since delta is less than 0, we have complex solutions. So you will see now that k1, the roots to these equations are k1 and 2 are sorry, so it is minus 1, it is plus 1, plus or minus e times the square root of negative delta all over 2, which is equal to 1/2 plus minus e the square root of 3 over 2. So this is the complex solutions. Okay. So the general solution would be something like this. So the general solution yg is equal to exponential, the real part 1 over 2 times x times now c1 times cosine of, now here comes the beta, which is square root of 3 over 2 times x plus another constant c2 times sine. The second one is the square root of 3 over 2 times x. So this is the general solution. Okay. Now remember that this problem, it is with initial conditions. Now we should find the value of C1 and C2. That satisfies, so we have y of 0 is equal to 1. This is the first initial condition. First initial condition. Now If you substitute 0 in x, what you get? So yg of 0 is equal to exponential 1 over 2 uh, times 0 c1 cosine of square root of 3 over 2 times 0 plus c2 sine square root of 3 over 2 times 0. Okay, so remember that exponential 0 is equal to 1, and here we have cosine of 0. Cosine of 0 is 1, so we have c1 times 1, and the sine of 0 is equal to 0, so we have 0 times c2. So the remaining, so g of 0 is equal actually to c1, and we have the initial condition is equal to 1, so indeed c1 is equal to 1. So the next thing is the derivative of the general solution at point x equals 0 is equal to 2. So now we compute the next constant. So g prime is actually equals, sorry, so we compute g prime. So again, what is the derivative of g prime? Let's compute the derivative of g prime, then we substitute with 0. Remember, if you have a substitution, you should first compute the derivative, then you substitute x equals to 0. If you substitute first, then you get a constant number, and the derivative of constant number is always equals to 0. And this is a common mistake that the students do at the exams. So be careful. So now we compute we compute the derivative of our general solution. Let's copy it first. So copy. So this is, we put it here. So we should take the derivative of this guy here. So let's take the derivative of this guy. So let's compute it. It is equal to we have multiplication of two functions, so it is equal to exponential 1 over 2x. What is the derivative of this guy? It is 1 over 2 times the remaining, the same thing, plus now exponential 1 over 2x times the derivative of this one. The derivative of cosine is simply minus sine. So and remember that we have inside the square root of 3 over 2, so it will be something like this: minus the square root over 2 c1 sine square root of 3 over 2x, and the derivative of sine is cosine, so it is equal to plus the square root of 3 over 2 times c2 cosine square root of 3 over 2x. Okay, now we do the we sum all together, so we get we factor out exponential 1 over 2x, so we have cosine of the square root of 3 over 2x multiplied by, so in the first one we get 1/2, it is c1 over 2 plus, and the second one it is plus the square root of 3 over 2 times C2, okay, plus now sine square root of 3 over 2 x times, so it is multiplied by, it is a half C2 minus the square root of 3 over 2 times C1, okay. So this is the derivative of the second of the general solution. Now we compute it at x equals 0. So this is equal to 1, and the cosine, of course, cosine 0 is 1, so this is equal to 1, and this sine is equal to 0, so this guy uh, will be cancelled. What remains is so 1 times 1, so this is indeed equal to C1 over 2 plus the square root of 3 over 2 times C2, and we have that y, sorry, the general solution prime at 0 is equal to 2. So this is a given information. So this leads us to C1 over 2 plus square root of 3 over 2 times C2 is actually equal to 2. Now remember that C1, we did compute C1 before, and we found C1 is equal to 1. So 1 over 2 plus square root of 3 over 2, C2 is equal to 2. So this gives you that, so we solve this equation with respect to C2, so C2 is equal to 2 minus 1 over 2 all over square root of 3 over 2, and this is equal, so the first one will give you 3 halves times, now the inverse is 2 over square root of 3, these 2 will cancel, 3 over the square root of 3 is equal to square root of 3, so C1 is equal to 1, and C2 is equal to square root of 3, and the particular solution that solves this initial condition problem is y is equal to exponential 1/2 x times, now we have 1 times cosine the square root of 3 over 2 x plus now C2, which is the square root of 3 times sine square root of 3 over 2 x, and this is the particular solution that we are looking for. So this is the particular solution that we are looking for to our problem here, which is this problem. I will copy it down. So copy. So this is the solution to this problem. So this is, yes, do you have, yes, yes, Timothy. What is the question, Timothy? Yes. C2 should be 3 over 3. So C2 is equal to 3 over the square root of 3, like this. Yeah, but 3 is equal to the square root of 3 times square root of 3. So these two cancel together, what remains is this guy. Okay? No problem now. So now let's see. So this is the particular solution to this problem, and also it satisfies these two initial conditions. These are the initial conditions. Okay, so we move on now to the next problem. I think we stop here. Do you have any questions, or you would to continue? You would like to continue? Who wants to continue and who wants to stop? What? I didn't understand you, Rila. You want to continue or stop? Ah, yes. Yes, yes. Thank you. Thank you. That's a lot. So, thank you for attending. Tomorrow we continue to the next problems of exercise number 8. Thank you for attending, for your attention.